Number 4 says how many milliliters of a 0.800 molar sodium hydroxide solution is needed to just neutralize 40 milliliters of a 0.600 molar hydrochloric acid solution. Okay, straight up equation right in time. We've got sodium hydroxide plus hydrochloric acid going to react together to form our aqueous salt, sodium chloride, and liquid water. As we look to balance this equation, you'll note that it's already balanced as written. Therefore, all of our coefficients are coefficients of 1, which you don't have to write in, but I'm going to, just to help me visualize what's going on here. Our next step then is to determine how many moles of hydrochloric acid we start with. To do that, we need to use our formula for molarity, which is moles per liter. Our concentration is 0.600 molar. Our volume in liters is 0.04000, which means that our number of moles of HCl in solution is 0.02400 moles of HCl. That also means 0.02400 moles of HCl. That we've got the same number of moles of sodium hydroxide because the relationship in the balanced equation is 1-to-1. Therefore, we also have 0.02400 moles of sodium hydroxide. And we've had a lot of fun, but we haven't really answered the question. We're trying to determine how many milliliters of 0.8 molar sodium hydroxide solution is needed. So we're going to come back to our molarity formula. We now know how many moles we need of the sodium hydroxide solution. All we need to do now is figure out what volume we need. So 0.02400 moles over X. Watch out here. You're actually going to be dividing your 0.02400 by 0.8 to get 0.0300 liters, or 30.00 milliliters of NaOH required. Boom! All right, and our final set of problems for the day, number 5 and 6, we're asked to assign oxidation states to each of the atoms in the following reactions, and then identify the atoms that undergo reduction or oxidation. So as we take a look at question number 5, element, bam, oxidation state is 0. Element, bam, oxidation state is 0. We've got a neutral compound here, water, which means the sum of the oxidation numbers must equal 0. Again, the oxidation state of oxygen in most cases, including this one, is going to be -2. Hydrogen is going to be +1, and look how that works out. 2 hydrogens each at +1, 1 oxygen at -2, means the sum of these oxidation numbers is going to equal 0. Now, as we think about the atoms that undergo reduction or oxidation, hydrogen is oxidized. Put here Leo. In other words, hydrogen has lost electrons. It went from an oxidation state of 0 to an oxidation state of +1, which means it must have lost negative charge. So hydrogen is oxidized, oxygen is reduced. Grr. In order for oxygen to go from an oxidation state of 0 to -2, it must have gained electrons. So in this example, hydrogen is oxidized, oxygen is reduced. Okay, same thing, different equation, a little bit more complicated here, which will give you a good opportunity to practice writing in your oxidation states. We're going to start by doing the easy ones. Oxygen is going to be -2. Hydrogen is going to be +1. -2. Okay, let's take a quick look here. The overall charge of the sum of all of the oxidation states here has to be -1. If I've got 4 oxygens, each with a -2, -2, -2, -2, what charge then must the manganese atom have so that when you add it to -8 will give you an overall charge of -1? Well, it must be +7. So manganese is +7. As we look then at your oxalate ion here, C2O42-, the overall charge has to be -2. We've got 4 oxygens, each with a charge of -2, and we've got 2 carbons. So what must the charge of those 2 carbons be so that when you add them to the charge of -8, we get an overall charge of -2? Hopefully we can, in our minds, figure out that it must be +3. And so we've assigned oxidation states to everything on the reactant side of our equation. We come over to the product side. The manganese ion here is just +2. That's a lot easier. Oxygen here is -2. We've got 2 of them, -2, -2. Here, the overall charge has to equal 0, so that means carbon is going to be +4. Water, oxygen is -2. Water overall charge has got to be 0. Oxygen is -2. That means hydrogen must be +1. Okay, now we've got to figure out what has been oxidized, what has been reduced. As we scan our oxidation numbers, manganese has gone from a +7 to a +2. That tells me that manganese is reduced. Grr. It must have gained electrons to go from a +7 to a +2. As I continue to scan my oxidation states, I note that carbon goes from a +3 to a +4. That means carbon is oxidized, or LEO. It must have lost electrons to go from a +3 to a +4 oxidation state. All right, and then the last thing I want you to keep in mind is you take a look at these reactions on the last page here. Question number 3 talks about essentially precipitation reactions, or as an example of a precipitation reaction. Question number 4 is looking at an acid-base reaction, and then your last 2 reactions there are example of redox reactions. So again, be able to identify each of those 3 different types of reactions, or look at a set of reactions and classify them as one of those 3.